So thank you for letting me speak here today. So we'll go back to the AGB phase, binary AGB phase as well. Wait, my microphone doesn't stick. Yeah. So I'm at the end of my PhD, so I'm gonna talk a bit about the highlights of the 4 years of my PhD, in which I have been studying the AGB wind companion interactions, but through hydrodynamic models. Okay, so this is also the postcard of atomium that Marie already showed you, which proves that the outflows of AGB stars are not spherically symmetric, and that there's a lot of structures of which we think many of them are caused by the impact of a companion that is orbiting around the AGB star and is influencing the winds. So yeah, we also see in population synthesis that it is okay to assume that many of these stars will be in binaries. And if we include planets, then this goes up to about 100% percentage of which AGB stars have companions, and planets can also have an impact on these winds. So this also shows that we have to be very careful if we use results in which the 1D assumption is used, because if we have these deviations from spherical symmetry, this will impact our estimates of, for example, mass loss rates. So it is important that we study the impact of this companion and of these 3D asymmetries. So this is the most technical thing I'm going to show about the model I'm using. So I'm using the Phantom code, which is developed by Daniel Price here in Melbourne. We have an AGB star and a companion that are just sync particles, so gravity-only particles. We don't model the star itself. And then we have a free wind of SPH particles that are launched from around the AGB star. And because we cannot model the pulsations and dust and all the fancy things that they do with the cobalt codes, we have to artificially balance the gravity of the AGB star, and that way we can more easily launch the winds. So then we model some cooling, H1 atomic line cooling, which is included in the equation I showed there. That is to cool down the region around the companion, because if we don't include this cooling, we get super high temperatures and weird things happening in the simulations. And as I said, we don't have yet the pulsations, dust nucleation, and approximate radiation. A lot of ongoing work is still going on to include more physics in our models, but I'm still using the rather basic implementation there. Doesn't look too promising. Okay, that's a shame, because there's still a lot of movies coming. But yeah, this slide is fine. So if we have a companion that is orbiting around the AGB star in the wind, we generally create nice spiral structures in the wind, and that is twofold. There is the companion that is gravitationally attracting material, and in this way is creating a spiral. But then you also have the orbital motion of the AGB star around the center of mass, and because of this orbital motion, you also tend to create a spiral structure. And then in general, the impact of a companion will be stronger if its mass is larger, because it can gravitationally attract more particles. If it's closer towards the AGB star, so smaller to a major axis, because it enters regions with larger density. And then if we lower the wind velocity, the impact will also be stronger, because the kinetic energy of the wind will be less strong. So it tends to move away from a companion less, so the companion can gravitationally attract more material. And then we can also include orbital eccentricity, and this also complicates a lot of things. So in the simulations I have, we have a 1.5 solar mass AGB star with a solar mass companion at a separation of 6 astronomical units, and then the mass rate is set to 10 to the minus 7 solar masses per year. And then we're going to study the impact of the wind velocity. So we range it between these 3 values. And we also study the impact of orbital eccentricity. Okay, so in these images you see here, you see the density distribution in a slice through the orbital plane in case of 2 different wind velocities. And what you see is that in both these cases, a nice Archimedes-like spiral structure forms in this orbital plane view. And if you zoom in a bit more on this one, like I did here, you see that here the companion is attached by one structure behind it, and there is a second bow shock structure in front of it. And the other one, it's just a two-edged spiral structure. So you have these two different options. Then if you rotate the view and you look edge-on, the structures look quite different. So instead of an Archimedes spiral, if you look at the cross-section, you have arc structures or ring-like structures. Oops, oh, sorry, yeah. In the lower velocity model, you see that the ring-like structures are a bit more elongated. This elongation is due to the orbital motion of the AGB star. So you have the forces directed in the orbital plane, and that is why you see that these rings are so elongated. And this effect will be stronger if the wind velocity is lower, because then this relative effect of the orbital velocity is larger. And now it's movies again. But it's all the same type of movies, so if they don't work here, it's not gonna work. But yeah. The basic idea is that if you include eccentricity, you get a lot more asymmetric density distribution, so you get much weirder shapes coming. If you have a high wind velocity, then you still have a sort of Archimedes spiral, but it becomes asymmetric. And you have at one side, the spirals are like moving quite fast, and they run into each other quite fast, and everything gets a bit vague. While on the other side, the spirals are much thinner, so the inner edge and the outer edge of this two-edged spiral is closer together. And in that way, you get gaps in between two follow-up spirals. And that's what we call low-density gaps. And then because you have these low-density gaps, you also have regions where, I can show it here, where you go from a low density gap region to two regions where the spirals overlap. And there you have two spirals that seem to run into each other, and that's what we call bifurcations. And those had also already been shown in the literature to be typical things for eccentric morphologies. And then if you lower the wind velocity, you get much more extreme weird structures that arise, and then there's no more symmetry at all and no more regular things. Okay, let's see. Okay, now that we have included this H1 cooling, as I told in the beginning, we get the formation of accretion disks in our simulations. So what you need to get accretion disks is this efficient cooling around the companion, otherwise material just will be pumped away by high pressure and high temperatures. And then you also need to set the accretion radius small enough. So in our case, it sometimes had to be as small as 0.01 AU for an accretion disk to be able to form. But we see that if you put the accretion disk small enough, you'll always form an accretion disk around the companion. And then you also need high enough resolution to resolve the disks nicely and see the shapes. So here you see what these disks look like. So in the lower right corner, you see the temperature distribution. This is in the orbital plane slice. And you see that the temperatures are still quite high. They still go up to 10 to the 4th Kelvin, although we have, even with this H1 cooling. And then in the other side, you see in the big square the orbital plane density distribution, and the other two are the edge-on density distributions. And there you see that the disk has a flared shape. So if we look a bit closer, we have here two disks in case of a different wind velocity. So in the left one, this is the one with the lower wind velocity of these two. The disk will be larger than in the higher wind velocity. You can see the radius is about up to 0.5 in the case of the higher wind velocity, and can reach up to 1 AU radius in the case of lower wind velocity. Yeah, so that's the main difference. We see that it's much bigger. And then here you see the velocity structures, velocity distribution within the disks. The most easy one to understand is the tangential velocity distribution. So this is again in the orbital plane. And you see that material is orbiting around the companion swing particle in the center quite fast. And if you compare it to the Keplerian velocity fields, as you do in the graph here, we see that material is orbiting almost at the Keplerian velocity. And this clearly shows that we have actual accretion disks where material is orbiting around the star. And then if you look at the radial velocity, first you can note that the velocities are way smaller than the tangential velocity, so only up to about 40 kilometers per second instead of up to more than 200 kilometers per second. And you see that we have a blue side and a red side around the disk. And that is because in the red side, material is moving a little bit away from the companion, and in the blue side, material is moving a little bit towards the companion, which means that you have sort of an eccentric orbit within this disk. But if we look at one radius and we take the mean of all these velocities, you still see that material is slowly going towards the companion. So it's slowly being accreted onto the companion. And then we also see that there are some spiral structures in the disks. If I put them away again and put them again, they're not that easy to see, but we see them as density-enhanced structures. Okay, and then finally, we also studied what the impact is if you have a triple system. So we only look at hierarchical triples in a coplanar states, such that we don't have Liouville quasi cycles and things like that. So we keep it as simple as possible. So you have an inner binary, the AGB is there with a close companion, and then we add a tertiary companion. And because of this third mass, you also get that the inner binary is orbiting around the common center of mass, and this will all complicate things a bit. So these are the parameters that we have. We vary the wind velocity again to see what the impact is of that. And we also vary the mass of the outer companion. But these are again movies, so I'll just have to say shortly again what we see. So the main thing we see is that you have a spiral structure from the inner binary, like we had in the previous things. And then when you add a tertiary companion, this creates an additional spiral on top of this inner binary spiral. And this spiral is also has a waved outer pattern because it interacts all the time with these spiral shocks from the inner binary. And then the inner binary spiral is also rotating around the common center of mass. And that makes that you have some sort of a snail pattern because it's a spiral that is rotating. So those are the main points. Yeah, we also compared one of our triple simulations to the observations of the star Aquila, which is known to be a very complex morphology, which might be shaped by a triple system. So we used the radiative transfer code Magritte to create these synthetic observables, and we tried to see if there is some sort of a match. But we don't want to make a really hard one-to-one comparison because there's so many uncertainties about what could be one or multiple companions around Aquila, because not much is known about this star except for that the structures are extremely complex. So the main conclusion here is also that it could be this type of systems, but we don't see any hard constraints that there is indeed a triple shaping these outflows. So we need some observers to really look deeper into the morphologies that we see in Aquila. And that was all I wanted to say. So I'll leave it's 2 questions. Thank you.
Thank you, Jolien.
So you mentioned the H1 cooling. Is the molecular line cooling ever important?
Yes, it is important, but it's not yet included, but it will be soon, I hope. Yes, but so now we regulate the temperature with gamma set to 1.2, which is in between isothermal and adiabatic, and we know that's not going to be perfect for sure. So it could be that if we include more realistic cooling, that's the full wind will be cooled down a bit more by this molecular cooling, but yeah, it's difficult to get like the exact right temperature profile, but yeah.
Okay, thanks.
More a suggestion than a question, since your videos didn't work. Maybe you can upload them to the Slack.
Yeah.
Then we can all enjoy them.
Good.
So I have one. So you in your model, you model the companion is about 1 solar mass. And what about other lower mass substellar companion? What do we expect the effect will be on the spirals? Or
yeah. So it's about the companion mass. Right? Yeah, so if you lower the companion mass, you will always get like more regular structure. So you rather go to a two-edged, nice Archimedes spiral instead of having these bow shocks. But Silke also once made a model with a companion that is only about 10 Jupiter masses, I think. And even then you also saw that there was like this nice thin Archimedes spiral structure in the wind. It might be more difficult to resolve with observations, giving the noise and stuff like that. And the density contrast just becomes like lower, but you still get a nice Archimedes spiral.